Hi everyone, I wanted to do an example where we use the concept of center of mass to solve a problem that I think will be similar to at least one of your homework problems. So the problem we have here is that we have a boat. It's 5 meters long, 150 kilograms, and it's sitting in the water with a 75 kilogram pirate in the back of the boat. So it's this guy. And the pirate is going to walk to the front of the boat to try to get off the boat and onto the dock. But if the boat's not tied up, what's going to happen to the boat when the pirate walks from the back to the front? So I drew a little picture here, and I always recommend that you draw a picture or a diagram with your homework problems, especially if there isn't one provided. It can be really helpful for visualizing the situation. And this problem, the concept of center of mass is really useful here. CM for center of mass, because we have a problem that has a system of two objects. There's a boat and a pirate, and we can consider the behavior of the system just by thinking about the position of the center of mass. And so in this case, we have our system of objects, the boat and the pirate, and they only exert forces on each other, like when the pirate's walking back and forth, and there are no external forces acting on it. Like, we assume there's no real friction with the water. And so therefore, even though the pirate and the boat might exert forces on each other, the center of mass of the boat and pirate system shouldn't move at all. So let's start by calculating where the center of mass should be for this system. And I started out and I took the liberty of assigning a coordinate system. So I said the front of the boat is here at x equals 0. And since the boat's 5 meters long, I said the back of the boat is here at 5 meters. Now, you could choose to define a slightly different coordinate system. You might flip the back and the front, but you should get the same qualitative result to describe what happens to the boat. So we'll assume that the boat has its mass uniformly distributed throughout from front to back, and we'll treat the pirate like a point particle that just sits on the back of the boat. And so if it were just the boat, then we'd say the center of mass would be like right here in the center of the boat. But since we have the pirate sitting on the back, that sort of shifts the center of mass. So we say we expect the center of mass to be probably somewhere over here, closer to the pirate. And we can calculate exactly where the center of mass is by using the formula. So m1 x1 plus m2 x2 over m1 plus m2, where here m1 and m2 are the masses of the boat and the mass of the pirate, and x1 and x2 are the position of the boat and the position of the pirate. So the mass of the boat is 150 kilograms, and for the position of the boat, or the x-coordinate of the boat, let's just use the average position, which is the middle of the boat right here, which is at 2.5 meters. Then we have the mass of the pirate, 75 kilograms, and the position of the pirate is at 5 meters. Divide that by the total mass of the pirate plus the boat is 150 plus 75 kilograms, so 225 kilograms. And we find that the center of mass should be at 3.3 meters. So I'll write that in here. I think it's actually 3.3333333 meters. Okay, so sometime later, let me draw a second diagram. Later, here's the dock. Here's x equals 0. If the pirate moves to the left, then in order for the center of mass to stay in the same place, the boat has to move to the right. So the boat's actually going to end up like somewhere over here. And the pirate is going to be here. And the pirate's sad because he was trying to get off and onto the dock, but now he doesn't get to. Poor guy. Or she. I guess I shouldn't be sexist. Could be a female pirate. Okay. So that's no good. So if the pirate moves left, the boat has to move right, and the center of mass position of the system has to be in exactly the same place. And so for a qualitative description of what happens, that's sufficient. If we wanted a quantitative description, then we could do something like define, how far the boat moved. Call that delta x maybe. How far did the boat move? Oh, I don't know. I would like to know. Here, let's see. I guess there's a couple different ways to approach this. You could write out the expression again for center of mass using this unknown delta x, or you could think about the symmetry of the system and say, well, this situation down here is really similar to the situation above. It's just flipped. Now the pirate is at the front rather than the back of the boat. So if we do a little analysis of what it means on top when the center of mass is 3.33 meters in x, that means that this distance is 3.3 meters. And this distance is 5 minus that, or 1.67 meters. And so when the pirate moves to the other end of the boat, now we know that this distance must be 1.67 meters, and this distance must be 3.3 meters. And so in order for the position of the center of mass to still be at 3.33 meters in x, then this delta x here must equal 3.33 meters minus 1.67 meters, or also 1.67 or 1.666 meters. So 1.67 meters plus or minus 0.01. So for our final answer, we could say the boat moves away from the dock when the pirate moves forward. The boat moves backwards by 1.67 meters. Okay, so I hope this helps. Have a good night.